Lesson 12.4, Inverse Matrices. You can use matrices to solve a linear system other than using Cramer's rule. To do that, though, we're going to need to know how to find inverse matrices. The identity matrix multiplied with any other matrix of the same dimension equals the original matrix. So the identity matrix is just multiplying, that doesn't do anything. So matrix A times the identity, or the identity times matrix A, equals just matrix A. So like multiplying by 1. So it's the matrix equivalent of 1. And here are two examples. Notice we have 1s on the downward diagonal, and everything else is a 0. So we could actually have it bigger if we wanted. It is always square. The downward diagonal is 1s, everything else is a 0. Turns out you cannot divide by a matrix. So let's say you had an equation of 2x equals 4. If you can't divide, what would you do? Well, we would multiply by, say, 2 to the negative 1, which is 1/2. Well, we're going to do the same type of thing. If we multiply a matrix by its inverse, this negative 1 means inverse. It equals the identity matrix, which is like doing anything. Just like x times x to the negative 1 is 1. So if a, b, and x are matrices, ax equals b. I want to get rid of the a, so usually we divide, but we can't divide by a matrix, so we'll multiply by the inverse. Remember, matrix multiplication, the order is important. So since I put the inverse matrix on the left of the left side, it also needs to be on the left of the right side. So at the beginning of both sides. It needs to be in the same place on both sides. And I put it here on the left, so it's right next to the matrix A. So they will end up essentially canceling out. They make this identity matrix. And the identity matrix times anything is just that anything. So if we start with a times x equals b, x would be the inverse of a times b. All right, so how do we find the inverse? Well, here's the rule for the 2 by 2 matrix, which you should memorize. If our matrix is A, B, C, D, then the inverse is 1 divided by the determinant of A, B, C, D times this mixed up matrix. So what happened? The downward diagonal traded places, and the upward diagonal has changed signs. So memorize that little formula. All right, so let's find the inverse matrix of 1, 2, 3, 4. So we're going to start by filling in the formula. It's 1 divided by the determinant times mixing it up. So the downward diagonal trades places. The upward diagonal changes sign. So that's 4 minus 6. And of course, 4 minus 6 is negative 2. And then distribute that to everything. So we'll have negative 2, 1, 3 over 2, negative 1 over 2. And that is the inverse. Let's try another. Okay, to find the inverse, it's 1 over the determinant times the mixed up matrix. Downward diagonal trades places. Upward diagonals changing signs, so it'll be a -4 and a +1. Find the determinant, so it'll be 0 minus -4. So that's 1/4. And distribute the 1/4. So we'll have 0, 1/4, -1, and -1/2. All right, so let's solve a matrix equation. So if we're in the form A times x equals B, here's matrix times x equals a matrix. So to solve this equation, we need to get rid of matrix A by multiplying by its inverse. So we need to find the inverse of matrix A, that one. All right, so it'll be 1 over the determinant times, mixing up the matrix, downward diagonal trades places, upward diagonal changes sign. The determinant is 21 minus 20. So our inverse is -7, -4, -5, -3. All right, now that we've found the inverse, we'll multiply both sides of our equation by the inverse. Notice I've put the inverse first on both sides. So on my matrix equation, I've put the inverse first on both sides. On the left side, those are going to cancel each other. On the right side, we need to multiply these. So if I do the first row, first column, I'll have -7 times 3 plus 4 times -4 times 2. First row, second column, I'll have -7 times 8 plus -4 times -2. And then I can do second row, first column, -5 times 3 plus -3 times 2. And then second row, second column, -5 times 8 plus -3 times -2. Combine those together, we get -29, -48, -21, and -34. And that is our matrix X. All right, I promised that we'd use matrices to solve a system of linear equations. So here's my system of equations. But we're going to write these as matrices. So the first matrix is going to be the coefficients, the 2, 1, 1, -3, and then the variables, and then the constants. But this is in the form AX equals B. So we're going to solve it the same way we just solved our last one. Start by finding the inverse of the coefficient matrix. All right, so it'll be 1 over the determinant times, mixing it up, downward diagonal trades places, upward diagonal changes sign. It's -6 minus 1. It's -7. And to try to avoid using as many fractions as possible, I'm going to leave that as my inverse. I'm not going to multiply through with a negative 1/7 yet. We'll get to it eventually. All right, so now we have the inverse. We're going to multiply the front of both sides by that inverse. So the left side, remember, is going to cancel out to become xy. The right side then is our inverse that we had just found times the constants. And since the inverse was on the left of the left side, it'll be on the left of the right side too at the beginning. All right, I'm going to multiply the matrices first. So first row, first column, negative 3 times 13 is 39 plus negative 1 times 11. And then the second row, first column, negative 1 times 13 plus 2 times 11. Which gets me 28 and 35. When I multiply it by negative 1/7, so now we'll distribute, I get negative 4 and negative 5. So my answers, so that was x, y. So my answer is negative 4, negative 5 solves a system of equations.